So that should be fine, yes.
So now it might appear a message in the screen saying that this is, and then in the tablet you can say, okay, I'm okay with the recording.
Lo tengo.
Okay, so for now we are set up. Just wait for the people to come.
Okay.
Nice. Your surname is supposed to be with the umlaut, isn't it? Or not?
Which one?
Your surname.
I said no, no.
Ah, all right.
It's bird in German.
Good. Okay. Sorry, for whatever reason I thought it was.
Yeah. There's probably some version where they write it differently instead of no.
They're called Julia Bird.
Yeah.
Like Larry Bird.
Exactly.
You play basketball?
Like Larry.
Yeah.
Where are you from, Julia?
Germany.
But which part of Germany?
The southern part. It's well, originally from a small village right between Stuttgart and Munich, the two big cities in the south. But I studied in Freiburg in the Black Forest. That's where I did my PhD.
Okay. I was living in, I lived in Bonn for 3 years.
Oh, okay. Nice.
This time, no jokes about the fact that Bavaria is actually not real Germany.
No, these jokes are more fun with Bavarian, yeah, pressing.
Or Germans anyway.
Yeah. No, I spent 12 years in the United States. I got used to being politically correct, because everybody's offended.
The Lawrence Law, you see, which part of California is it?
Close to San Francisco.
Okay.
A little more. It's like 70-kilometer landingwards, pretty much just landingwards from San Francisco.
Okay.
And you have two labs there. You have the Berkeley National Lab, which is
Right.
at Berkeley, and then Livermore. Yeah, it's one of the two big weapons labs that worked on the Manhattan Project back in the days. Livermore and Los Alamos.
Okay. I only knew about Los Alamos.
Yeah, they did work together. I mean, most of the work was done in Los Alamos because that's where the scientists were stationed.
Yeah. You don't think? Even the speaker left.
Entonces, claro, sí, o sea, olvídate, el comité unitario hasta después del verano.
Entonces no me interesa. Si era de vacaciones. Sí. Is your computer going to sleep? Right. Okay.
Let me do anything.
This is the classical technical glitch just at the moment of starting the.
Congratulations.
It's a tradition.
Yes, we can start. So it is my pleasure to introduce Julia Vogel, who's visiting us today from the Centro de Astropartículas y Física de Altas Energías de la Universidad de Zaragoza. Julia did a PhD in Freiburg in the Black Forest, and then she did a first postdoc in Freiburg itself, and then she moved for 12 years to Lawrence Lab, California. She's been working mostly on X-ray missions, X-ray optics, and she's going to speak. Well, I guess most of what she's going to speak about is going to be YAXO, where she's the deputy spokesperson, and she's the chair, correct, of the optics group. So yeah, and somehow we were speaking about how poetic is the relationship of X-ray astronomy and the sun. So yeah, it's going to be an interesting talk.
Thank you. And thanks for having me in your seminar series. It's always nice to see Carol. And I'm happy to be here. So I'm going to talk to you today about the dark side of the universe. So looking for dark matter via searching for axions that originate in the sun. So we're using helioscopes to do that. So I'm going to talk a bit about the different aspects of that. So first, this is a brief outline of my talk. I'm going to give a brief introduction or some introduction to dark matter and axions, because I assume that's not something everybody is working with every day. Then I'm going to dive a little bit deeper in one type of axions, the solar axions, and how we could detect them. We'll see that axions can be categorized according to their origin. They could be produced nowadays in stars. They could have been produced early in the universe, shortly after the Big Bang, or we could produce them in the laboratory ourselves today. So we're going to look at the parts where they are produced in the sun or in the core of stars in general. Then I give you a brief overview of the previous helioscopes, so previous axion searches for solar axions, and the state of the art, which is the CERN Axion Solar Telescope, or short CAST experiment, located at CERN in Geneva, Switzerland. And then I'll head over to the next generation of this experiment, the IAXO experiment, the International Axion Observatory. That's in the moving towards its construction phase, and better said, we're moving towards the construction phase of the intermediate step, which is baby IAXO, so a first step towards the big IAXO experiment. And before I conclude, I will tell you about the physics prospects of this next generation experiments. So let's start out with dark matter. So what is dark matter? This is like the simplest picture. So you probably, most of you are looking more for the light part. We're looking for the dark side of things. So basically everything that doesn't emit radiation and only interacts via gravitation. So very feeble interactions. It's very difficult, which makes it very difficult to detect. So why do we even want to look for these dark matter? Well, there are various different observations, and they hint at the fact that the majority of the mass in the universe, or the majority of the mass in the universe, cannot be observed directly because there is no emission of electromagnetic radiation, and therefore this matter has been referred to as dark matter or invisible matter. So as I said, there's no radiation signature. We only have interaction via gravity, and that's for about 85% of matter. On the right side here, you see an image of Hubble image of the Abel cluster, galaxy cluster, Abel 1689. And overlaid in the light, you can see that would be the distribution of the dark matter that is expected for this galaxy. So we're gonna look at a few reasons why we need dark matter. That will use Newton. We can use Newton for rotational curves. Einstein when we look more towards gravitational lensing. That's reason for why we need dark matter. So we have to use indirect information because we cannot directly see dark matter. And already as early as 1933, the first one to actually look at these dark matter was Fritz Zwicky. So he studied the velocities of galaxies in the Coma cluster, and he realized that there was not enough matter that could be seen in order to explain the motions. So he concluded that there was 400 times the mass necessary, 400 times the mass that we could see in that galaxy was necessary to explain the motions. In reality, it's more like a factor of 10, but it was not really his fault because the Hubble constant at the time was just really off. So it was his calculations in principle were pretty good, but he was just using the up-to-date constant at the time, which wasn't very good. So this dark matter keeps the galaxies together without contributing to the luminosity. The problem was that Fritz Zwicky was very difficult to work with. He was not really very collegial and at odds with most of his colleagues. So they tended to not take his theories too seriously, which is a pity because it took quite some time, namely till 1967, till Vera Rubin studied galactic rotation curves. And to estimate the radius to estimate the mass as a function of the radius in spiral galaxies. So you're probably all very familiar with this. Like you can measure the velocities of spiral galaxies by looking at blue and red shifted wavelengths as compared to the center. And then if we equate the centrifugal force and the gravitational force, we should get a stable system. And when we do that, we expect rotational velocities that are inversely proportional to the square root of the radius on our solar disk where we are. So what that would look like in Kepler motion would be something like that. You would expect that the further you go from the center, the slower you get, so which is the left picture here. What was observed by Vera Rubin, however, was that the velocity is pretty much constant after a while. So it increases to a certain point, and then it stays pretty much constant up to the outer arms of the spiral galaxy. So from this, we can back calculate how much mass we actually have in the spiral galaxies. And it turns out we get to that factor of about 10 that Zwicky would have gotten if we wouldn't have had the wrong Hubble constant. So we need 10 times more matter than we can see in these galaxies. So that is one of the big hints why we need dark matter. It's pretty difficult to explain these rotation curves if we do not. Do I touch something again? No, exactly. Unless we start modifying Newton gravity. So, for example, there's a so-called Mond theory, which has a whole lot of consequences if we use it. This is the best explanation. We just have more mass than we can see. There are other indications for dark matter. For example, looking at the cosmic microwave background, it would look very different if we had only matter, but dark matter influences this distribution differently. So from the observations we have, we need more matter than the one we can see in there. Another hint on dark matter we get from structure formation in the galaxy when we're on large scales. So you got these clumping effects and you get some voids. And if we don't have the dark matter, these structures can just not be reproduced in any of the simulations. It also gives us actually more information that we need these dark matter needs to actually be cold dark matter rather than hot dark matter, which would be light particles at relativistic speeds. So for example, neutrinos could be in principle dark matter, but they would be hot relativistic, so they could only be hot dark matter. And if all the dark matter was hot dark matter and neutrinos, these structures would be way more washed out. So we wouldn't see the structures as we see them. So neutrinos could contribute to the dark matter, but only a very small part. And then there's another hint, that's where Einstein's theories come into play, that's gravitational lensing. So if we observe, for example, a cluster of galaxies that will be over here, you have a big mass in between, then you can see that space-time is bent and the light will follow a curved, this curved line. So you can imagine space-time like a stretched sheet. So you put a heavy mass, the sheet is dented, and that's the way the light will also go. So there is a really short animation. So from these observations that have been made, we can conclude that there must be a big mass between the galaxy we want to observe and the observer. So, but we can't see that mass, so that is a strong indication for dark matter. By the way, most of these dark matter slides I stole from my colleague Laura Borders. She does really nice dark matter intro talks and WIMP talks. If you're interested, you should look at it. Okay, so we now know that we need dark matter, or we want to have dark matter, because all the other explanations we have make things very, very complicated. So let's start with what we have. We have the standard model of particle physics. So these are all, you're familiar with that, is all the particles that we have, quarks, fermions, everything in there. We have our neutrinos in there as well. It's an extremely successful theory that explains many observations up to energies of about 1,000 times the proton mass. However, it's really an effective theory in the sense that it's like the lower energy limit of a theory of everything. So it's almost a theory of everything, or a theory of almost everything. So we expect observations of new phenomena when we go to higher energies, which is what people are probing at the Large Hadron Collider at CERN in Geneva, Switzerland, where they shoot protons at high speeds together and hope to discover physics beyond the standard model. This model, while widely successful, has some major flaws. It unifies only 3 of the 4 fundamental forces, so gravity is not included. It also doesn't include a particle that could account for the dark matter. We have the neutrinos, but as we saw before, they could only account for a small component of the dark matter. There are other problems with the standard model, like for example, some constants are just kind of fixed randomly, I mean, at a certain value without us being able to explain why. There are some problems in quantum chromodynamics, and we're going to come back to that in a bit. That it's called the strong CP problem. So it's a problem with charge parity symmetry. And that's where one of our particles, the axion, will come in. Okay, so we have to go outside our standard model in order to look for our dark matter. And how much of this dark matter are we actually looking for? So the normal matter, the baryonic matter that we all know, stars, us, everything, is about 5% of the matter density in the universe. And you can see that stars are around 10% of these 5% of normal matter. We have some genus in there and gas. Around 27% are these dark matter that we're talking about today. And then 68% is dark energy, where we have even less clue, or theoreticians have their theories, but less understanding of what dark matter could be. So we're going to focus on the dark matter for today. So what kind of particles outside the standard model could there be? So this is our standard model of particles. Well, theoreticians have been very creative, and there is a whole zoo of possible candidates. But there are two which are the two favorite candidates, and these are weakly interacting massive particles, or WIMPs, and the axion. Historically, WIMPs have been kind of favored. There are a lot of WIMP searches. And this is mostly due to the fact that the lightest supersymmetric particle would be a WIMP. So these WIMP searches kind of aligned with like a trend in physics, because people wanted to study supersymmetry, for example, at the LHC. There are a lot of WIMP searches, and the way these WIMP searches work, so these are heavy particles, and basically these searches use the fact that a WIMP could collide with an atomic nucleus and then produce a recoil, and that recoil we could detect via heat, light, or charge, depending. There are a lot of different experiments that make use of that. But we're not going to look at these WIMP searches, because these WIMP searches, there are many, and they've been rapidly closing in and without in their window where the WIMPs could exist, and they haven't found anything. So in recent years, the axion has been moved more to the spotlight. There is a priori no reason why all the matter should be WIMP or all the dark matter should be axions. It could also be a mixture of different particles, WIMP, axions, or any other particles. Like the standard model has many different particles. Okay, so we're going to focus in this talk on the axion. So what is an axion in a nutshell? I told you before there is a so-called strong CP problem in the standard model that the standard model cannot solve. So in quantum chromodynamics, so the theory of strong interactions, we expect a violation of charge parity symmetry. So basically, charge parity symmetry, you have a particle, you mirror it at the origin and replace it by its antiparticle. And then you check if the same laws of physics apply. From the theory and the Lagrangian, we have a term that's CP violating, which looks like this. So we expect this symmetry to be violated. But that would imply that we get a theta parameter in the standard model that is very, very tiny. And there's no real reason why this should be tiny, because it can be principally between 0 and 2 pi if we don't observe that. So we expect it from the theory. So there is a theta parameter, but we cannot observe it experimentally. It could be observed in the electric dipole moment of the neutron, for example, that also contains these theta parameters. But again, these measurements show that these theta parameters would be extremely small for no obvious reason. But an elegant solution to this problem is replacing this variable theta with a field and make it a dynamic variable. So this adds another term in our Lagrangian, and this new field is called the axion field. So basically, you introduce a new symmetry, you turn it into a dynamic variable, and that's relaxes automatically to 0, and you wouldn't expect anymore to see CP violation, as is observed. When this new symmetry is spontaneously broken, we get a pseudo-Goldstone boson, and that would be the axion. But we don't know the breaking scale, so that could be rather random. There's nothing that fixes that problem. So this is our new candidate. In principle, the axion is introduced to solve the problem of the standard model of particle physics. It will be an extremely weakly coupled fundamental pseudoscalar particle. And it has a generic coupling to 2 photons. So in all axion models, you always have a 2-photon coupling. There are more complicated models where you also have coupling to fermions, electrons. You can have also couplings to nucleons. But in all the models, you have generically a coupling to 2 photons. The mass, however, of this particle is unknown. This has to do with, we don't know the mass, we just know it's proportional to its to the coupling of the particle, the axion to photon. This, why we don't know that is because we don't know this breaking field, so these two are related. What we can do is we can do from astrophysical observation from certain stars and how these axions would be produced in these stars, we can conclude that there is an upper limit on this coupling constant, and it should be smaller than 10 to the minus 10 per GeV. All these properties make this axion an ideal candidate for dark matter because it's basically not interacting, it's light, and it could be, we could have a lot of them. So they could make up for the dark matter. So originally it was introduced to solve a problem in strong quantum chromodynamics, but it could also be a dark matter candidate. I think I said most of that actually. So it's an elegant solution to the axion is an elegant solution to the strong CP problem. They're very weakly interacting, and the nice thing is they were not introduced to just solve dark matter, but they have a different origin. They can address. There are several astrophysical hints that we can address. So, for example, on Earth we see too many high energy gamma rays. We wouldn't expect so many to arrive from faraway objects to to Earth, basically. But with axions, we could explain why we see so many, because axions can basically travel further without being observed. And then are some observations of anomalous stellar cooling, for example, in white dwarfs. So axions there could provide an additional energy loss channel. So there is the relevant parameter space for these dark matter axions is at reach of current and near future experiments. And we're still intensifying the efforts to look for these particles because so far there's still more WIMP search than axion search, although that field is growing. There's also a whole bunch of other particles. They're called axion-like particles. So basically, if we take away this condition that the mass is proportional to the coupling constant, we can still solve the dark matter problem. We just wouldn't solve strong CP anymore. So that's a bit more generic particles. Okay, so let's go into solar axion detections now that we killed 2 birds with 1 stone. I mentioned before that axions are often, or actually experiments are often categorized by the origin of the axions. So these relic axions are the ones that have been produced shortly after the Big Bang. Then we have lab axions where we produce them ourselves with a strong laser magnetic field. I should have mentioned that before, so let's go quickly back. So how these axions are produced is we have axion and we have a virtual, couples to a virtual photon from an electromagnetic field, so it can be a field or an electric field, and out we get a photon basically. So that's the so-called Primakov effect and the most important coupling that's generic in all these models. So when we produce them in the lab, all we basically need is a strong light source, like a laser, and a magnetic field, a strong one, and then we can produce our own axion. And then we have the solar axions. In principle, they could these axions could be produced in the core of stars in general, where we have dense plasma and photons. But the sun is the closest one, so that's the easiest for us to observe. So there are a bunch of experiments for each of these categories, and we're going to focus on this part down here. These experiments for the relic axions, they're very sensitive, but in a very narrow mass range, and they have a high dependency on models, which means they usually assume that axions make up all of the dark matter. As I mentioned before, there is no theoretical reason why they actually should do that. The lab axions have a very low model dependency. We produce the axions, we detect them. And for solar axions, there's some model dependency because of the solar models we're using. But usually the axion production rates are very robust and don't depend much on them. So for the top ones, we have new ideas. For the last one, they're ready to scale up. But in general, these are all complementary experiments. So how do we produce these axions in the sun? Well, in the core of the sun, we have black body photons. They are in the keV range, so X-ray photons. And since we have the plasma there, we have strong electromagnetic fields, and we can have these Primakov effects. So we have the black body photon and a virtual photon from our plasma, and now we would get axions, which then could basically travel out of the sun because they don't really interact, and we could detect them on Earth. This is kind of like, this is how the axion flux in the sun would look like. It's basically like a Planck spectrum because that's what we have in photons in the core of the sun. And this here gives you an idea of what that flux is. We have a dependence of on the coupling constant square, so axion to photon coupling constant, and we also have a dependence on energy. So that was the simplest case where axions only couple to photons. But if they also couple to electrons, for example, then the case gets more interesting, but also a bit more complicated. So that's kind of like the secondary level of axion model. In this case, in addition to these Primakov axions from axion-photon coupling, we also have ABC axions, as we call them. It's shown here in red, and these could be about a factor of 100 more intense. So this is the spectrum we saw before, the Planck-like spectrum. And this one has been already multiplied by a factor of 50, just so that you can still see it, basically. So this was what gave us the Planck-like spectrum. And then here are the additional effects. We have complement effect, branch doubling effect, axion recombination, axion re-excitation, and so on. So basically everything you can normally have with electrons as well. So this, if you want to go to more complicated models, that might be, it's a possibility. There are also other couplings, as I mentioned before. So we can have axion-nucleon couplings, for example. That usually gives us monochromatic lines, similar to what we just saw in the spectrum as well. We have the lines on top of the spectrum. For example, there is a possibility of seeing 14.4 kV line from axions that are emitted in an M1 transition of iron 57 nuclei in the sun. And there are other materials that could also, other nuclear transitions that could also give us specific lines if there's axion-nucleon. So this is how the axions are produced. So now how do we detect them in axion helioscopes? The first axion helioscopes was proposed back already in 1983 by Pierre Szekely. And basically we're using the same process that's used in the sun, which is using the inverse process, basically. So we have our axions produced in the sun, they can escape the sun and fly to Earth. And there we set up a strong transverse magnetic field to match the quantum numbers. Axion come in, we have a virtual photon provided by the field, and out comes another photon, which again has the same energy as our original, due to energy conservation. So we get out an X-ray photon, and we just need to put an X-ray detector at the end to look for them. This idea was refined a few years later by Calvin Weber and colleagues. So what they suggested is to fill this region here with a buffer gas. And like that, the photon in there can acquire, this photon here basically acquires an effective mass. And we can see axions of larger masses. And we'll see in a second why that is. That is the so-called coherence condition that can be restored. This is how the probability of reconverting axions into photons looks. As before with the flux production, we had a factor of the coupling constant squared in there. So we also have that in the reconversion. You can also see that the B field we're using, the strength of that B field matters. And the length of that B field is in various places hidden in here. There are some other factors in here. So the gamma is an absorption factor. So if we have a gas in there, we have absorption. And then we have the momentum transfer between the axion and the photon, which is basically the difference in the mass between the two. And if we're in a vacuum, this term would just go away because our photon mass would be zero. So let's look quickly at the vacuum case, because I think it's really instructive to explain this coherence condition. We can simplify that equation I just showed you. Get it in this form of a sine square over x, sine square x over x squared, with x being QL half. First, what we see is the B is important, the B field, and the length of the B field is important. But if we plot this function, you can see it looks something like that. So you get most of the contributions if you had values of your QL hat that are smaller than, let's say, 1. It's not an exact science, you could say small 1 pi, small 1, but in any case for small value. So this gives us our coherence condition. So we will only get significant conversion of axions into photons, back conversion of axions into photons, if we can keep this term small. The length of our magnet is usually given, so we have to keep this momentum transfer small. And you can see in this case, there is not much we can do. We're just going to be sensitive up to a small axion mass, and then this condition will no longer be fulfilled, and we will just not see anything. But if we fill a buffer gas in there, we have to use the full momentum transfer. So in order to get this Q small, this difference has to be small. So we're giving our photon an effective mass, which is illustrated here. It depends on mostly on the density of the gas we're putting in. And then we can basically get this value small around a certain axion mass. So we can probe around a certain axion mass. And this is shown over here. So this is the number of expected photons as a function of the axion mass. In vacuum, we're only sensitive to small masses, and then we won't see much anymore, just because of that sine square x over x square function. And then if we fill in buffer gas, we can restore this coherence around a very narrow mass range. And by changing this density, by changing the pressure of the gas in our magnet, we can scan this peak here along the masses and basically go in small steps and check different axion masses, because remember, we do not know the mass of the axion. So how to make a helioscope that's effective? We've already know we need a magnet and we need an X-ray detector. So these are the two main components. But there's a third one we will need if we want to go to a next generation, and this is X-ray optics. So we need X-ray optics to focus our few photons from axion conversion on a small detector, because this will allow us to use a very low background detector. The larger our detector, the larger our background. And here it shows our sensitivity. So obviously we want to detect as an axion, but if we can't see it, this gives us an idea of how our sensitivity is. So we said before, production goes with GA gamma squared, and also the reconversion. So we have a total of a dependency in our sensitivity with a coupling to the 4th power. So we want to get this small because we want to go to really weak couplings. And you can see that, again, the B field and the B field and the length of the magnetic field are important. Also the cross-sectional area of our magnet, and to some degree the exposure time. Usually we use more exposure is always better, but in this case, it is better, but it only increases our sensitivity slowly. Our X-ray optics, we want to focus on a very small spot with very high efficiency. And the detector should have low background and a high detection efficiency. So we're looking for something like 1 background event per year. That's what we're aiming for in background. So typically between 2 generations of these helioscopes experiments, we got an improvement in sensitivity to GA gamma of the order of 7. And the next generation, we're aiming for 1 to 1.5 orders in sensitivity, which corresponds to a factor in signal to noise of 10 to 20K. So it's quite a big step. There are some other searches, I should have said. So this one is basically working like a telescope. It can be moved to follow the sun. So when it looks at the sun, we would expect a signal. When we look away from the sun and our field is not perpendicular to the incoming axions, then we would expect no signal. And like that, we can compare like a signal over no signal data. There are some other potential searches, like one can make these helioscopes stationary, then you would just basically see a modulation signal. And there you could also use crystalline detectors. So using, instead of a B field, using the crystal's electromagnetic field or electric fields. But these experiments are not as sensitive because these fields are just not as strong as the magnetic fields we can use. And there are some more exotic experiments that can look especially for electron exonucleon alone. Okay, so what has been done in terms of helioscopes and what is the state of the art? I'm not kidding you. This is the real logo of the first axion helioscope, the Tokyo Axion Helioscope Sumiko. And on the bottom, that's the state of the art, the CERN Axion Solar Telescope. So you'll see that's the field of a LHC dipole magnet that's used. And originally, the experiment was called the solar axion telescope antenna, or in short, Satan. But nobody wanted to fund the devil, so we renamed it to CAST. It was a very short-lived name, but the logo stayed. Okay, so the very, very first generation, actually, before the Tokyo Helioscope was built at Brookhaven, but it was just a few hours of data. It was just a proof of principle. There were not like significant limits derived from that, no axion detected, obviously. But the first real installation of a helioscope was this Tokyo Helioscope Sumiku. And here's like a setup. So we had an X-ray detector, no optics, just a magnet. So just a magnet and detector on a platform that was movable and could observe the sun from minus 30 degrees, so 30 degrees below the horizon, till 30 degrees. Below the horizon, dark matter, we don't care. It goes through the Earth, so we don't really actually need to see the sun. We just need to point to it. And that's pretty much how the experiment is actually. This is the state of the art, the CERN Axion Solar Telescope. It actually just concluded this year. It's the most powerful axion helioscope to date, and it has been running for more than 20 years. Its core piece is a decommissioned prototype LHC magnet. So that's a 10 Tesla superconducting magnet, a 9 Tesla superconducting magnet of 10-meter length. It's one of the first ones. So the accelerator uses the big accelerator uses bent magnets, and that's one of the first test magnets that's a straight magnet with 2 bores. We also have some X-ray focusing devices. Not all bores are equipped with that. And we use low background techniques, so new detectors and new background reduction techniques. The solar tracking with this one was only possible for 1.5 hours in the morning and 1.5 hours in the evening. So we can only tilt it by plus minus 7 degrees, not quite as far as Sumiku, but still way more sensitive than Sumiku. This has to do with the superconducting magnet. If you tilt it too much, you quench the magnet basically. First data was taken in vacuum, 2003-4, and then there was a gas run that took 6 years. It was a bit more work to install that. And then there were improved vacuum runs with better detectors, and so on, as well as some experiments of the Helioscope type. So they're looking for the halo axions as well. So these were installed as well. And some dark energy candidate searches as well. So the way this works is in the morning, this side is east. So the axions would enter from this side, are converted in the magnet, and then can be detected by what we call the sunrise detectors. And even in the other way around, the sun is here, conversion and detection on the other side. So we don't have to turn the whole thing around. And this is how it looks in action. Let's see if that works. So that is, of course, a time lapse. The whole tracking from down to up takes about 1.5 hours. And then it's moved quicker to a parking position where it can then acquire background. That would just another view when you sit on top of the magnet. Let's see one more. This is sort of tracking the sun, and then moving to a parking position. And maybe the next one, I think we can see our little window that we also have in the hall. No. So there is a little window in the hall through which we can actually twice a year check if we're really looking as so optically observe the sun to see, you can see it over here where it gets bright, where we can actually optically check that we're really looking at the sun, but mostly we're relying on surveyors for the orientation of the magnet. In this helioscope, we produce some benchmark limits for solar axions with the help of a prototype for the next generation experiment, so the IAXO Pathfinder that was installed there. So we installed a small optic. This is a part of a nuclear spectroscopic telescope array, NuSTAR optic. That's from the NuSTAR NASA SMACS mission. And we also use the latest generation of our detectors. What we use is gaseous detectors, micromegas detectors. So it's an evolution of a TPC, a time projection chamber, with a micromesh readout. So basically, you have amplification in your gas, and then you can detect your ionized particles. So there are a lot of things going into that. So they have to be very compact, They have to be very well shielded. In this case, we are above ground. We're not going underground. And the materials have to be very radio-pure, so they are all measured for not having intrinsic radioactivity. And that delivered the best experimental limit on axions, axion photon coupling over a wide mass range, namely 0.66 times 10 to the minus 10. 10 to the minus 10 was also the astrophysical limit, so that was the first experiment able to compete with these limits. And it's shown over here. So this is a typical plot when we do not see an axion. That's an exclusion plot. So you have the axion mass here, the axion photon coupling on the y-axis. In this yellow band is where we would find the axions that solve strong CP and can be dark matter. Outside, there would be the ALPs, the axion-like particles. So as you can see, we probed here into this, we probed a big chunk of this model. This was the initial runs, and that down here in red is the improved limit, and you can connect that. So this part is the vacuum phase, and this wiki part is basically the scanning through different pressure settings. Okay, so where are we going from here? I just said CAST concluded in 2023. So the next step is the International Axion Observatory, and this is what we envision it to look like. It's mature technology, but also like state of the art. And it's based around a purpose-built large-scale superconducting magnet that resembles the Atlas configuration at the LHC. So it's a toroidal geometry. It's going to be 20 meters long and 5.4 Tesla field. So less than CAST in field, but longer. And we will get to a 300 times the figure of merit than compared to CAST, because of the fact that we have 8 conversion bores with each having a diameter of 60 centimeters. CAST had bores of a diameter of about 4 centimeters, and only 2 of those. We are going to have these 8 detection lines. You can see them here in gray. Axial optics that focus on a 0.2 square centimeters focal spot, and then we have the detectors in the focal point. Ultra low background, and the setup will allow for a tracking time of about 50%. This is kind of like $100 million, 100 million euro scale project. You can use dollar or euro, I think it doesn't really matter. So our approach was, let's do a smaller version first. Work to devise, if you're naming an experiment and you do not want to get a lot of invitations to congresses on female reproductive health, do not name your experiment baby anything. But there we are. And this is what baby IAXO is going to look like. So it's an intermediate stage for IAXO. It's on one hand a technological prototype, which features a slightly smaller magnet. It's 10 meters. But the bore size will be actually larger than IAXO, 70 centimeters as compared to the 16 centimeters emission for IAXO. And therefore, the optics and detector systems are going to be close to the final IAXO one. So we'll be able to upscale the magnet and basically use the technology we developed for X-ray optics and detectors. And the neat thing, it's not just a technological prototype, it will also have a relevant physics outcome because it's already a factor of 10 better than CAST in the B squared L square and A figure of merit. So the magnetic parameters, basically the magnet parameters. How does that magnet look like? Down here, this is going to be the IAXO magnet. I get back to that in a second. So it's called a common coil configuration. So basically our bores in which we observe and which we have the automatic fields are shown here. And they're sandwiched between 2 of these racetrack assembly that create the field. The field that will look something like this. So these are the racetracks. It's a frontal view cut through the system. So our racetracks are these ones, and here we have our bores. The whole IAXO setup is then this toroidal configuration where we still have our racetracks and our bores, but just in that slightly different configuration. We want to make it cost effective and with little risk, so we can start as soon as possible. And it's best, of course, to use the existing infrastructure that's already there at CERN. We have some issues with the production of the aluminum stabilized superconducting cable right now. It's just worldwide. There was one company who could do it. They're located in Russia. You can imagine the rest of the story. So currently, multiple experiments are struggling to convince industry, for example, to build these cables again. And there is work in progress. The whole CERN management is involved in that too, because all the experiments need this cable. In terms of the optics, the needs we have for baby axion, I said before, we want to have a high throughput efficiency. What we can get to with X-ray optics is 40 to 60%. We have to tune it to the axion spectrum and the detector response. It's no use if we have a good response for our optic where we don't expect the axions, obviously. And we can enhance these with multi-layer coating. So for X-ray optics, we have very shallow incidence angles. And for that reason, we have to multi-layer coat them. So we get on different coatings, coating layers, we get direct reflections and can add up our signal. We also want a small focal spot area. I said before, that's around the area we have, which adds up to a radius at our focal spot of 2.5 millimeter. That's relatively modest spatial resolution in terms of space talk. And we want a moderate focal length because we don't make the experiment too big. So the modest spatial resolution, because we're looking at a big block, we're looking at the sun, and it's 10% of the sun that produces most of the axion. And we want it cost effective, obviously. If you have to build 8 of these optics of 70 centimeter diameter, you want to make that as cheap as possible. The considerations we're using for our optic, we want to make a hybrid optic with a core part of either prism aluminum foil optics or Mustar flow and segmented glass optics. And the outer part comprises also segmented optics, but in this type, the glass is cold slump. And that was a technology developed by the Italians for Athena. So the baseline we're going to use one XMM flight sphere optic that already exists and matches the parameters for Iaxo pretty well. So like that, we can focus on just having to build one optic and optimize that one. And that is that hybrid optic, as I told you. In this case, it has a Mustar-like core and the outer cold slump glass core to build it to that size. Why that? First, we can test 2 technologies. Second, that's exactly the size Mustar was already built to. So that's something that is safe and easy to build. We did also some of these coding tests already for the outer part. So basically what this glass, the segmented glass, is like your laptop screen glass or the one that is used for the bendable phones. So you coat it when it's flat, then you bend it into the shape you need it. And you, of course, don't want to destroy your coating. So we did some tests with that, and pre and post bending, the coating works just the same. So it's we don't introduce additional stress for our requirements. The detectors we want to use, we need very low background. In our units, that means something of the level 10 to the minus 7, 10 to the minus 8 counts per keV square centimeter in second, around 1 background count per year. We already demonstrated in CAST that we can get to 8 times 10 to the minus 7. And the ground at Canfranc, we demonstrated we can get down to 10 to the minus 7. But we will be semi-above ground. So we're going to be in an accelerator hall, but it's not very deep. So we will not be at confront levels, obviously. So we have to still optimize that to actually achieve the 10 to the minus 7 at least above ground. So that's work in progress. We want a high detection efficiency. We also would like low energy threshold, because if you remember these axion electron spectrum with the many spikes on it, it was shifted to kind of low energies, below 1 keV. And we would ideally also want good energy resolution. But the most important first is to find the axion, and for that we need a low background detectors. And the only ones that can do that so far is our micromegas technology that we're going to use. But we're also working on additional technologies which promise to have very low energy threshold and energy resolution, such as metallic magnetic calorimeters, transition X sensors, SEDs, and grid-pix, which is a further evolution of the micromegas detector, so basically the pixel-like readout. This is where we are going to build baby Iaxo. We're going to build it at Daisy, Hamburg. There used to be a proton electron accelerator, so we have a big hall underground. This one is meanwhile empty, and that's where baby Iaxo is going to fit nicely into it. And we're going to reuse the supported drive on a medium-sized telescope from the CERN telescope array that was set up as a prototype in Berlin. And it's already at Daisy now, so we're going to refurbish that to be able to move that heavy magnet. And we expect that we will be able to commission with the magnet in about 5 years. Okay, let me quickly tell you before I conclude what the physics prospects for these experiments, IAXO and baby IAXO are. That means once we take off the cap and can hopefully see dark matter. This is obviously we have a discovery potential and we're hoping to discover the axion. But if we cannot find the axion, this is the sensitivity we expect. Again, our exclusion plot, axion mass versus axion photon coupling. With baby IAXO, so I should start with half maybe. This is the current best limit. Here again, model bands. With baby IAXO, we get 10 times the magnet figure of merit and can get down to 10 to the minus 11. With IAXO, we improve the magnet figure of merit by 300 and get in that 10 to the minus 12 range. And ideally, if everything goes well and we can push the magnet a bit more, the optics a bit more, and the detectors a bit more, we could eventually get to the IAXO plus configuration. And with that, we could probe large areas here of this QCD axion space where they solve strong CP and our dark matter. They're just like these are just two typical models. One just axion photon interaction, the other also axion electron interactions. They are all used. And from theory also, there's this region up here. If we find a particle up there, it could at the same time solve the dark matter and also inflation. So that's called the ALP miracle. That would be a nice region to find it. There's another well-motivated region down here. So that I mentioned before that when some of the white dwarfs in cooling, there have been some anomalies. It's not definitive. It could just be statistics and other things as well. But one possible explanation would be axions could provide an additional energy loss channel for these objects, especially if we have axion-electron interaction. So that would be in that range. And then we have these transparency hints, why we see high energy gamma rays that shouldn't make it all the way to Earth at Earth. So in the interstellar magnetic fields, we could convert these photons into axions. They could travel less disturbed or not be absorbed. And like that, closer to Earth, they could reconvert into photons and we could still see them here, even though they come from really far away. And then we have like a whole range in between roughly these two lines, so this whole area here, where we don't necessarily solve the QCD problem, but this would be axion-like particles that can still solve the dark matter problem. So we address different directions. We address theory, we have astrophysical hints that we can probe, and cosmology predictions. So with that, let me show you real brief the IAXO collaboration. We're about 125 scientists from 22 full members and 5 associate institutes. As you can see, we also have SETCA members in our collaboration. And with that, we're always hunting for more members and ask them to come to the dark side. We don't quite have the axions yet, but we definitely have coffee and cookies. So with that, let me conclude. After we figured out all our fields, if they're really parallel, it's always an interesting discussion. So axions and ALP could solve the dark matter problem, which is an important issue and beyond the standard model physics. So we kind of need this dark matter unless we come up with some better ideas. Helioscopes can search for axions and ALPs produced in the sun over a very wide mass range. I didn't really show you helioscopes, but the helioscopes can probe very deep, so they're very sensitive, go to low couplings, but only in very, very tiny mass ranges. The current best limit on Primakov axions was obtained by CAST, that's the Nature publication. Baby IAXO is in addition to go one order of magnitude below, not quite 1 order of magnitude, 10 to the minus 11. And with IAXO and IAXO plus, we could push it 1 to 1.5 orders of magnitude or below the current sensitivity of CAST. Obviously, we hope to find the axion somewhere there, but this is definitely significantly closing in on the window in which axions could still exist. There's the physics reach, QCD axions, so the models where you also solve strong CP, axion-like particles that come naturally into play in a lot of theories like string theory, astrophysical hints that we've seen, like the anomalous like warp pooling. There are other things I didn't talk about. There could be dark radiation or dark energy candidate searches, and the plan is also to implement helioscopes inside one or two of the IAXO bores to look for these axions that were produced shortly after the Big Bang. Down here again, one more time, IAXO, baby IAXO, and we photoshopped it already at DAISY. That's the big IAXO that probably would have to be above ground just because it's too big to fit in one of the halls on the ground. And with that, thank you very much. And we always keep one pack of axions. So they actually were named, axions were named by the Nobel Prize winner Frank Wilczek after washing detergent because they clean up a problem in QCD. So we always keep a pack close. So we've already found them in some way. Thank you for your attention.
Questions? Andres?
Thank you, Julia. Very, very interesting talk. It's very far away from my expertise, so please bear with me.
Sure.
So during the production of actions, photons are involved. I guess because you don't know the mass of the action, you really don't know what is the energy of those photons. It could be.
No, the energy we know. So the energy we expect it to be X-ray photons, just like in the core of the sun, because you conserve the energy. But the mass we don't know because the mass is linked to the coupling and to this breaking scale of this new symmetry that we introduce to basically produce the axions.
But then my question would be like, would it be possible that this production of actions could be indirectly seen in the X-ray photons that you are seeing in the sun? Like in the sense like, for example, if you are in the photon-nucleon combination, I saw that you had some peaks in the spectral distribution. Like, could that be observed as the effect of photons, X-ray photons in the spectrum, in the electromagnetic spectrum that we are observing in the sun, or some like features, I don't know, absorptions or something like that?
Yeah, so there are some approaches. So in principle, we always assume that the axions, they're produced in the core and then they just stream out as axions, so they don't recombine. But in principle, one could assume that in the outer parts of the sun, where you also have strong magnetic fields, or sunspots, for example, where you have really strong fields, you could get some reconversion. And basically, yes, you could look with X-ray telescopes in space for these signatures in X-rays directly. And that has actually, there is work ongoing with NuSTAR. The problem usually is you need a telescope that can look at the sun, but is also sensitive enough. So XMM or Chandra, the typical X-ray optics, they can't look at the sun. They tune for low photon counts because you want to be sensitive. So you would just burn the detectors most likely. NuSTAR is one of the few, unless you use the solar telescopes, you can also do that, but they're usually not so sensitive. So NuSTAR is actually your best guess for that, and there's work going on to do that. And it's actually, yeah, you would have a really nice signature because you would expect basically more an X-ray signature from these axions in the core of the sun. So because they're mostly produced in the core, so you would see kind of like an X-ray excess in the inner 10% of the core. And then you could also say, you could also look for, so it shouldn't change with time, for example, in principle. It should change if the magnetic field changes. It's a bit challenging in the sense that you have to model the solar field, the solar magnetic field. So in that, I've worked with solar physicists, and they keep telling me, why don't you find the axion and then we tell you what the field is for the So I said, no, we do it the other way around. You tell me what the field is and then we find the axion. But yeah, so it's a bit chicken and egg problem. But yeah, that's definitely something. The problem is the model uncertainty.
Thanks.
Antonio on the side.
Yep. I'm not an expert either, so maybe it's a silly question. But anyway, would you expect any background coming from the sun that could be confused with the expected action signal. For example, something related to solar gamma rays or neutrinos that somehow interact with your instrument.
That's an excellent question, actually. But no, it's not really a problem for us. The thing is that our magnet is light tight. So light cannot enter, we don't care. So only axions enter, and the only thing we can see is whatever comes out of the magnet. So everything's light tight and radiation tight, and the detectors are shielded, so we have no, in general, suppress all the background, be it natural radiation, be it something else. So yeah, you couldn't really get anything else in there. But yeah, in principle, that might be a problem if you do direct observations from satellites. If you really look for the X-rays, then yes, then you have all kinds of sources of background. But for these experiments, no, because we could also look through the Earth, for example, and like you wouldn't have X-rays or anything from the sun coming through.
I have two questions. First of all, thanks for the talk. It's actually great to see a different kind of telescope. I mean, it doesn't have a mirror, so how can it be a telescope? But that's
Well, this one does, but not like where you expect it to be.
not
Yeah.
what you expect it to be.
But it kind of looks like a telescope. I mean, it's like, right?
Yeah, it kind of looks like it.
It does look like a telescope.
So my question is, how upscalable is this design compared with our capabilities, right? For example, in optical astronomy, we decided, okay, a 10-meter mirror is not enough, let's make it 30, or let's send a bigger mirror in space,
Yeah.
and that gives us the orders of magnitude of difference in capabilities. Now we see that with IAXO compared to CAST, you're going to get about 2 orders of magnitude, 1.5. If you see, because we always say, okay, we need more data, or in case of particle physics, we need larger accelerators and more kilometers below Geneva. If you see that IAXO is not getting you the level that you want, how easy is to improve with existing technology, or how far away are we from getting better magnets, better lower background, more sensitive? All these components that you mentioned, is IAXO really top of the line? And to beat that, we need to wait 30 years, 10 years? Some comment on that?
Yeah, so I don't think it's the end of the line necessarily. So one could probably, till IAXO is built, I would assume, especially magnet technology is further along, and we can build stronger magnets, longer magnets, and larger diameter again. Because I mean, we're on a like 5-year timescale for commissioning for baby IAXO. Add another 10 years till we start commissioning IAXO, given that you need to build 8 optics and a humongous magnet. Till then, so you have at least like 15 years, 20 years. So you probably will have in all of these area improvements. So in terms of the magnet, I think there is still room to grow, especially in magnetic field strength. Maybe the size will be kind of like tricky. There is definitely room to grow also for the telescopes. You might work on the resolution, because that's more interesting once you see an axion, because then you want to know where exactly they come from in the sun. But the reflective coatings are constantly improved. So yes, you cannot go below 100%, obviously, but we're at 60%, so there is still room for improving that as well. Yeah, so I think that there is still room for a next generation brute force approach of the IAXO type. What is more of a problem is that, let me see where we have the exclusion plot. Let's go to the last one. There I have one where everything is in there. So in order to probe these models with helioscopes, that's going to be difficult, because you have to go really, really far down. And this part, the vacuum phase, normally, it's really, you can't push it really down with time. So just to give you this line is 2 years of measurement or year of measurement, and each point here is 1 day. So it goes to square root of 8 in our limit. So time to push this down here, you have to do something with like magnet and stuff like that, but it's tedious, so you won't get down here. But that's why we have these different approaches. So helioscopes are mostly at these higher masses where they probe these models. Helioscopes, I didn't really talk about those, but these are the ones they're using microwave cavities and basically getting a resonance. They're tuning them to different axion masses. And if you hit the axion mass with that tuned microwave cavity, you would get a resonance and you would see a signal. And these are the ones that are very sensitive, so they can probe very low, but you can see there's a logarithmic mass scale, so it's really tiny mass ranges. So they're really scanning forever to recover this mass range. But so they're approaching this window, to close that window on axions from the bottom, IXO and helioscopes from the top, and then these laser experiments where you produce your photons and then you detect them. They're called light shining through wall experiments, because you basically laser strong magnetic field produces your axions. You put a wall so that no X-ray photons go through or light goes through, and then you reconvert similar to CAST or AXO. They're currently at this level. They will probably also be able with better cavities to push down. Also challenging to get really to these levels down here, but they're making big steps because that's a relatively new technology. So the laboratory experiments were the last to join the game. So yes, basically what's the tricky part is this one. This is like what we call the window from hell. So this region over here, that's where the theoreticians like to put their favorite models usually. And we've also asked the question, so what if when we studied all the band, like, they're like, oh, no problem, we make the models a bit more complicated, we can still push it down. So it's the model, these are the simplest models. And the tendency is that nature favors more the simple stuff. But in principle, if you add more parameters, you can still like not infinitely push it down, but these could be wider than shown here. So yeah, it's the experiments over the next, let's say, 20 to 50 years should actually be able to close this window and either find the axion or exclude its existence.
It's a more philosophical one, the second. We can discuss it afterwards.
Okay.
Yeah, thank you a lot for the talk. It was very easy to follow for non-experts, so thanks. I have a kind of philosophical question too. So in your the standard model picture where you have all these particles, where would the axion fit?
The axion would be really outside of that because it's not part of the standard model, and for the reason because it only would interact with gravity via gravity, and gravity is not included in the unification. So it's really a particle that would be beyond that model, which is because this model is just almost
Sorry.
No, not at all. This is really just like, I mean, you can explain a lot with this model, but it's not a complete theory. So there is something missing already by the fact that gravity is not included. And several things cannot be explained. So there must be something beyond it. We just haven't found it yet. And they're like, accelerators are looking for it. Dark matter searchers are looking for this extra bit. But so far, let's say we haven't been sensitive enough. So we're working on it. So it would literally be like, here.
One. Since we have.
Yes.
Yeah, do you have questions?
No, I think they already.
I just want to
Ask.
make sure if the person connected online. Sergius, you had a philosophy. No. Ed.
Mine was a bit like follow up to his previous question. Like speaking of brute force approaches, what would be the effect of building like 100 Axions? Maybe putting them around the world, could it improve the resolution, or could it be just like observing a longer time with a single one?
No, you could combine the data. It would help you, yes, but given that like an IXO is of the scale of 100 million, it's kind of difficult. Like it's still not yet mainstream physics. So it's like, it's not an LHC, so it would be difficult. But yes, that would definitely help if you combine them, if you, yeah. In principle, the same as we did with CAST, we did several runs, and then you can just combine these limits and you get more and more sensitivity with that.
Because duplicating the telescope would, having another telescope would be paying the same price as of the first one. What I'm thinking is, first time we built an optical 4-meter telescope, that was massive thing. But now a 4-meter telescope, I don't want to say that you go to the supermarket and you buy it,
Yeah.
but it's significantly easier nowadays to build a 4-meter telescope.
Yeah, and the point with these X-ray telescopes, they still an enormous effort to build. I mean, I'm not. This is probably the same with the visible telescopes, but the problem is since you have these shallow grazing angles, so it's very, very tricky to get them coated. The coatings have to be extremely smooth. The mirrors have to be extremely polished. And to get at all like these efficiencies, you have to nest a lot of shells inside the other. They have to be extremely well aligned. So yes, it gets cheaper because in order to slump the glass into the right shape, you need molds, which is kind of like the expensive part. So once you've made one, you can reuse those for a couple of telescopes before you have to refurbish them. But so yeah, it gets cheaper. That's true. That's why we said, I mean, 8 is kind of random. It's like just like that magnet had 8 bores. That's kind of like easier to build because it resembles the Atlas magnet. So yeah, but yeah, in principle, it's true. You still need to build it. It's still some cost, but it's not as expensive as the first one. Which is why we're using space technology, because they have the instrumentation. Unless you scale it up. If you make the diameter larger, for example, we were looking into making a 70 centimeter new star-like optic, and then we just completely redo machining and stuff just because it gets too heavy. The glasses goes from 100 kilo to like I think 350 or something, and the machine just crashes. You can't use the aligning machine.
There was a philosophical question from Stelios, then Andres, and then
No, I'll leave the philosophical question because it might take a while. So, you can always.
Why do we need dark matter? Was that it? No. Why do we need dark matter? Was that the question?
No. It was actually about the axions themselves.
Okay.
If they are the hill to die on or not.
It depends. We just don't have many other good-looking candidates right now.
There goes the philosophical
There goes the
part of the
philosophical
question.
question,
If,
When people will tell
this
you no.
doesn't work, we are running out of candidates. And this has the advantage of being physically motivated, as you said, right?
Yeah.
So if at some point you call it quits, no matter what the theoreticians say about the complexity, yeah, sure, 3 parameters. Like what then?
Yeah,
We have a problem.
We do, yeah. We really need them to probably go to more complicated models. Have some theoreticians come up with more crazy ideas. They're normally not short of that, so usually it's,
even more crazy ideas.
even more crazy ideas, yeah. Yeah, but you might end up like introducing some ad hoc dark matter candidates without them solving anything else. But yeah, I mean, that's what it is. That's what it is. I mean, there's also the possibility, as for example, for WIMPs, at some point, all these experiments run into neutrino background, so they just not sensitive. Although models say in principle you could be below these limits, but you will never be able to observe them, at least not with these experiments. So it might be a matter of designing also different approaches, different experiments, which is happening in to address the window from hell. So there are a few exotic ideas out there how we could build other experiments than these 3 standard categories. But yeah, it's going to be interesting. I mean, it's job security if we don't find it. We need to find some other one. We really like to find it soon.
Mine was much more simple question. What about the lab experiments? You mentioned that they were also performing some experiments in laboratories, and
Yes.
that they were very simple to produce actions and detect them. Well, how is that going?
It's not going bad, but it's also, so that was the, sorry, I have to go to the end again. So that were these experiments. So most of these experiments came into being because there was an Italian experiment, which is called PV-LAS. And they see this one. And they claimed they thought they had seen a signal. But the signal was somewhere over here. So CAS already had long excluded it. Basically, what it meant is that the sun would have long burned out if we would have such a strong coupling. So it was just basically against everything, but it still was standing as a signal. So we were like, okay, we got to do something. And that's when all these laboratory experiments came into play. So it was actually Phoebe Lass was looking for something different and just accidentally stumbled over this. So then was when all these laboratory experiments started to be built. So that was maybe 10 years ago. The problem there is you need an extremely strong laser and, of course, a strong magnetic field. So the magnetic field is the same problem as helioscopes have, but the laser as well. So and you have twice this conversion as well. I mean, the sun is very efficient at producing these axions. If you have your laser producing yourself, it's harder to get the same amount of photons, basically. So these were the initial ones, but you can also see that in the short time of 10 years, that's where we're pushing now. So ALPS 2 is about to take data. So that will already be much more sensitive. Yes, so it's I think there's a lot of room for improvement for these experiments, as you can see in that leap between experiments in short time. But they also probably hitting a wall at some point because of like limitations in laser and there's like double production of axions and reconversion. So in both you lose, and that's what makes it tricky.
Thanks.
Sure.
All right. So guess we can leave it here. We thank the speaker again.
Okay.
The ones who have more philosophical questions, we are going to go for lunch at 1:30. So if you have philosophical questions that you wish to discuss over an orujo blanco, yeah, see you at 1:30. Juanete, ¿puedes